Welcome to our paper, Force Policy, Learning Hybrid Force Position Control Policy under Interaction Frame for Contact Twitch Manipulation. Think about inserting a charging plug. You first use vision to decide what to do next, where to move, how to approach, and how to line it up. As soon as you feel contact, you naturally set a contact structure, which directions to push and which directions to stay compliant. Then you coordinate force, compliance, and motion along those directions, and use force feedback to keep correcting the interaction until the plug is fully seated. Inspired by this process, we design a force policy that uses a general vision policy for global guidance in free space, and a high-frequency force policy to explicitly regulate the interaction structure during contacts. So the first question is, how do we define interaction structure and recover it from data? We define an interaction frame from the environment and the task intent. Local stiffness separates constrained directions from free ones. The intended force and motion anchor the axes, so the frame directly says where to push and where to yield. You can see this same structure across polishing, peg-in-hole, flipping, screw tightening, and scraping. Then we estimate it from demonstrations with two simple rules: subtract friction-like force when dissipation dominates, or subtract compliance motion when elasticity dominates. With the frame, we read in-frame signals to identify the contact mode and output control cues like a selection mask and a reference wrench. Now the second question is, how do we turn this into a clean global local organization for robot control? Our answer is a global local vision force policy. A global vision policy handles the big picture. It reads the scene, decides where to go and how to approach, and outputs a high-level action and a compact global context cue. Then a high-frequency local force policy takes over for interaction, and the key is that the local policy produces structured signals for contact, the interaction frame, a reference wrench, and a selection mask, along with the action. These are exactly the interaction structure signals we defined and recovered on the previous slide, and they give us the supervision to train the local policy to predict them. Finally, an asynchronous scheduler, with a simple router decides at each time step whether to stay with the global plan or hand over to local contact control, so we stay efficient in free space and stable and precise once contact begins. The core challenge is timing. The global vision policy is heavy, so its trajectory often arrives with latency, and directly switching to that delayed plane causes a visible jerk. We fix this with DTW-based chunk alignment by time-aligning the robot's recent execution with the newly predicted trajectory. This gives a clean transition point where we can drop stale waypoints, splice in the new plan smoothly, and resample everything to a unified 50 Hz. The aligned global commands then combine with the high-frequency local force outputs, so the hybrid force position controller always sees smooth, physically consistent inputs, especially through contact transitions. We evaluate 3 contact twitch tasks, where success depends on accurate force regulation, not just roughly correct motion. The table shows force policy performs best across all tasks, with the biggest gains in the most force-critical phases. The takeaway is that force feedback is genuinely useful, but only when it is integrated in a way that matches its intermittent, regime-dependent nature. Here are some evaluation videos showing force policy in action on these tasks. The key point is that force policy doesn't just succeed. It succeeds for the right reason, by regulating force in a controlled, timely way. On this task, it quickly detects contact and smoothly ramps up insertion force until the plug is fully seated, without overshooting or stalling, closely matching the force profile in human demonstrations. Here are the force profiles for the scraping task, comparing force policy with several baselines and human demonstrations. Force policy ramps up the contact force quickly, keeps it in the effective range through the critical scraping phase, and then releases cleanly at the end, closely matching the human force profile. By contrast, baselines tend to either jitter and lose contact, stay too weak to press down, or push in the wrong direction. Once contact isn't steady and properly loaded, scraping can't happen, and the rollout fails. We train on just one object with 50 demonstrations, then evaluate on unseen objects with different shapes and stiffness, and force policy still flips reliably by adapting its contact regulation rather than replaying a fixed motion. Baselines often break under these physical changes, while force policy keeps much higher success rates, even on harder cases like the sponge and cup. The takeaway is that explicitly modeling interaction structure improves robustness to real-world physical variation. Building on object generalization, we push the harder case, active, unpredictable interference. In this video, we intentionally jam the flip with a rod by pushing, twisting, and knocking the object out of alignment mid-action. The axes on the top right are the predicted interaction frame, And the key thing is how quickly they snap back after each disturbance. That means the policy is re-estimating the contact geometry on the fly, then immediately reorienting its force regulation in that frame, so it can stabilize the interaction and still finish the flip. Finally, here's why the asynchronous scheduler matters. It hides inference latency. With it on, action chunks stitch together smoothly for stable scraping. With it off, the robot hits stale waypoints and you see jerky resets, exactly matching the sharp velocity drops in the plot. That's all. Thanks for listening. For more details, please check our website.